which are able to be not based on precious commodities. And the catalyst, although I didn't have much time, but for example, this catalyst is not made out of precious material. This is based on oxides which are very abundant. So the one which I was talking to you, this was one which I think you can pretty well supply, I don't say the world, but pretty much you can supply a lot of people or countries to develop such technology. So that is one. But I agree that certain reactions most probably will be difficult to be done with non-noble elements, and then we will have issues to try to see if that we can do the reactions we want, and then it becomes an issue. But then we have a solution. Noble elements are often recycled. When we talk about this outmoded catalyst, what happens at the end of the outmoded catalyst? What happens here is actually a ring put. And then certain companies can even recycle as well. So that is the way we have to go. That means that we have to throw it away. And that also means that we as society will have to think about, when we think about material, that we always think in terms of, is it precious, is it recyclable, can we reuse it? So the principles which are there applies not only to carbon, it applies to any chemical element of the periodic table. Gosh, I'm afraid that's not my fault. But I think on that note, the progress through this evening's close. As I said earlier, if you are able to stick around for a little bit longer, maybe chat about who will be in the library, which is just through the doors to your right, otherwise it's leading you the stairs to your left. But thank you all again so much for coming, and thank you for a fantastic speech today. Good evening, ladies and gentlemen. In the next hour or so, I'd like to explain to you how chemistry can help to try to make our society more sustainable. There are three words: reduce, recycle, and reuse. And these concepts I'd like to explain together with catalysts. So tonight, I will explain to you what catalysts can bring us, what catalysts can allow us to do to make our society more sustainable. What I'd like to do is now is to start with a quote, an old quote, very good quote, but also a quote which has a real modern appeal, a modern concept: earth to earth, dust to dust, and I change something, carbon to carbon. And carbon is for chemists nothing else than this black ball, atoms, which you can connect. And carbon, you know most probably the best from this diamond. We always say diamonds forever. However, chemists know better. When you heat this up to very high temperature, then this carbon will be turned into carbon dioxide. And here you see the black atom of carbon, but now it's connected to two oxygen atoms. It's CO2. And this CO2 and carbon, they cycle. And they cycle, and we use it, we reuse it. Nature used it. Our society is built up from carbon. Me, all of you are carbon part at least. 23% of us is carbon. Just a lot. But currently, we are also having carbon dioxide issues. We know that carbon dioxide emissions are also something harming, that it's harming our society. So why is this? Because since years we are using another, although you can argue, also a precious form of carbon, fossil resources. This is coal, but also have natural gas. You have crude oil, which I will explain in a minute. And our society is built from this carbon. We have a lot of materials, plastics, fuels, and all contain carbon. Now carbon, we use a lot of it. We use a real lot of it. Do you know that we use about 90 to 100 million of barrels of crude oil per day? Now, 90 to 100 million barrels, it's about 160 liters. You cannot imagine, but I just put this here, it's stadium, about 7 of these will be full. So we use 7 of these per day. I'm not talking about natural gas, I'm not talking about coal. So we use a lot. Well, one can say then, do we have that already forever? No, not so. Because carbon, this crude oil, was discovered about in 1850, 1860. And this Colonel Drake, you like not Colonel, he discovered the first wells in Titusville, Pennsylvania, USA. In his first days, people did not know what to do with that black gold. What you can see in this slide is that it was used for a lot of things. Medical applications, diarrhea, whatever, things to try to cure diseases. The real first application for crude oil was lamp oil to light the houses in major cities like New York. And here in this picture which I took in the capital of Harrisburg State, Pennsylvania, you find this painting. And on the back you can see statues of where you drill the oil, the crude oil. And in front you see ladies holding lamps with filled with lamp oil. So this was the first real application of crude oil. So this crude oil was actually replacing the whale oil. So here in this advertisement in the newspaper, you can see that the whales were very happy when the crude oil was used for lamps, because they were not suffering anymore. So that is how it started. And then you think, well, lamp oil, I don't think I use it. And then we had Edison. And Edison was the discoverer of this light bulb. So light bulb, by electricity, replaced the lamp oil. And that is how it started. And then a very interesting quote which I would like to introduce here, that somehow the history repeats. And this is a hybrid car. 1917. This works with gasoline as well as with electricity. Now this car, 1917 company, was stopped its activity in 1918. So one can argue, why this hybrid car or electrical car did not take off? There's several reasons for it. But one of them was that, for example, the early batteries for iron nickel had a problem that when it was winter, they did not function properly, and that it was not properly working when it was cold. And second is that people did not consider that as very fancy. They wanted to have a car which made noise, because in these days car racing was getting very popular. So that made it that the car became a combustion engine. In 1900, when you think about the market share, number one was a steam engine car. Number two was an electric car. Number three was combustion engine car. This shows how the history somehow repeats itself. Now this introduction brings me then to now. This is what we use now. We know cars use fuels. This fuel. How is that done? Well, here I show in this picture the molecule, a very complex molecule. And a very complex molecule is a crude oil molecule which you will find in this barrel. This, if you would then put into your car will not ride very long. It will not function properly. And what this is a long chain. A long chain which I here have been showing with this representation. Black carbon, white hydrogen. But the first waste was, here I have a barrel of crude oil. And it was already mentioned that distillation can deliver you gin or Geneva, but it also can offer you different fractions. You have to remember the low molecule has a high boiling point. Small molecule has a low boiling point. So when you heat it up, you can separate it. In the first early years, we only used this upper part, the light, the small molecules. And the bottom part of crude oil barrels. As chemists, as industry, have been developing ways to cut these molecules into pieces. So when you see here this long molecule, you can use what I put here, a catalyst. And this catalyst is nothing else, something which allows you to break this bond. And by breaking this bond, this piece, you can put into your car, and you can drive the combustion engine. And what is now this catalyst? What is now this scissor? This device which allows you to cut up this molecule. Well, that's nothing else than this powder. And this is a catalyst. A catalyst is a substance you add to a reaction picture, and which will accelerate, speed up a process. It provides, almost literally, the scissors to cut crude oil, or molecules in general, into pieces. Now this thing, where you have crude oil, where you cut it, it's interesting to know that in the beginning the catalysts were not that great. In the beginning the catalysts actually, they produced fuel which was not that good yet. It also smelled badly. They had to add vanilla to it to get it better smelling. But over the years, I hope you admit, we don't have anymore a vanilla taste or smell, because we have been developing better catalysts which are able to use now every carbon almost of this barrel of crude oil. So this is how the crude oil, how the oil refinery, how we have been using our fossil resources to make our fuels, to make our plastics, to make our medicines, and also to do this. This is a picture from LA, Los Angeles, America. And you can see that you have here this brownish background, smoke, formation of bad air. And that brings me to a picture from a long time ago. I'm the one in that red circle. And this is on the right actually a fake picture, because in these days we did not have color pictures, just black and white. These things are trees which are dying. Trees are suffering from acid rain. However, if you would ask my children nowadays if they know what is acid rain, I doubt they know it, because we majorly solved the problem of acid rain. What is the reason why we had acid rain? It is because in this barrel we have not only the hydrogen and the carbon, but other elements. Elements like sulfur and nitrogen. And we have been removing the sulfur by making sulfur-free fuels, transportation fuels. And we have been removing the nitrogen because we have introduced a device. And the device which we have been using or introducing since the 1970s is this. And this is an old one, as you can see, €40, I bought it. And this device is nothing else than at the end between the engine and the exit of the outlet of your car, you put this device, which is a catalyst. And here you have noxious gases and harmless gases coming out. So you convert something which is poisonous to non-poisonous. If you would open this device, then you would see this honeycomb type device where you see you can go through, you can see through it. These holes are filled with material, with catalysts, which are able to bring in the noxious gas and transform them in non-noxious compounds, chemicals. I would like now to explain a bit what is a catalyst. But so far I just talked about a powder. So this is this device which I have in my hand. And now I would like to introduce to you some of the molecules and how a catalyst works. Catalysis is nothing else than surface chemistry. Chemistry at surfaces. And a surface is here this form. Salt. And a shoe is salt. You can also have, and I have water here in my hand, it's liquid salt. But here this gas, air here, it's a gas salt. So here we have a process going on at surfaces. And these surfaces, they are reactive. And you know it from corrosion, from rust. There's nothing else than surface process, where the surface is covered by iron oxide. Now here the same, so here we have different compounds, molecules, and I brought these molecules with me. Here I have a box with some molecules. So for example, when you have the noxious compounds coming from your car engine, is this molecule, which is CO, oxygen red, black is carbon. And here I have my CO2, you want to make out of this carbon, oxygen, oxygen. But there are also other noxious compounds besides CO, and it is NO. and NO2. Here now I have a blue nitrogen, oxygen, nitrogen, oxygen, oxygen. This one gives a brown color to the air. It's also toxic, and you want to remove them. So if we want now to remove these, and we want to make non-noxious compounds out of it, such as water and nitrogen, then we have to do something. We have to do something because we want to convert them. And the first reaction which we want to convert is the reaction where we have CO plus oxygen gives CO2. So what I did now is, I put here a big plate. And this plate is nothing else than the surface of a catalyst. And on top of it I put a metal nanoparticle. Now, I would like to dive into the world of molecules and atoms. I want to dive into the world which is really tiny and small. So this plate in reality would be 4 nanometer, 4 nanometer. Nanometer 10 to the minus 9 is 1 billionth of a meter. You can think, what is that now? So take a plane from London to New York. That's long distance. But what is then 1 billionth out of it? It's 0.5 centimeter, 5 millimeter. So this then is 2 centimeter, 2 centimeter. In the scale from here to New York. Pretty small, you agree? And this ball is 1 nanometer. That's small. And here, everything happens. So what happens is a reaction where CO plus oxygen reacts and makes CO2. So that's the first reaction, which is removing the noxious compound CO from the exhaust catalyst, as I show you in this picture. The second reaction is a reaction where we have to remove this NO, nitrogen oxide. Now if we would do that with oxygen, that will not work, because then we make an even worse molecule, NO2. So this NO, we have to react with CO, they combine, and they make then nitrogen. And that is non-noxious. So this is the catalyst which cuts and pastes, which is a scissor, but also which is bringing molecules together. So that is something what is happening, and we have not only this ball, we can also put another ball on it, another particle. I forgot to tell you that this particle is made out of noble metals. These noble metals are, as it states, are very expensive. Platinum, rhodium, palladium. Now this ball contains 55 atoms, and 13 of them are inside, does not see the surface. Remember, I told you about surface chemistry. So what happens is the chemistry happens at the surface. So we want to make these particles pretty small, because then all the atoms are surface atoms. But you can also notice that they have facets, and these different facets have different reactivity towards molecules. And that means that catalyst scientists, they are searching for the right particle, right in terms of size, right in terms of these facets exposed to the air, to the molecules it wants to destroy. So this is surface chemistry. This is catalysis. And I already explained that these are my children on the left. And they are at holiday in 2017, and this is a picture from LA last year. But you still see that it's not yet right. You can still see that this is not where you still would like to live in 2100. No. We still have to do something. Because this pollution also means that we will have to try to avoid things like the CO2 rise, which leads, for example, the melting of the ice and the level of the sea levels which are increasing. And now the molecule is not NO2 or SO2, but CO2. And we have now to make a new device, a new type of catalyst, a device which allows you now to take the CO2 out of the air and convert it into something useful, something where we can really try to do this recycling of carbon, carbon to carbon, CO2 removed. No one can argue and say, well, okay, it's not my business. So this is a picture which I took in a plane when I was flying to Canada. It's a flight to Calgary from Amsterdam. It was a flight with one of the most fuel-efficient planes. And what happens is that you are, of course, using fuel which comes mainly still from this barrel of crude oil. The emission, CO2 emission, from here, or let's say Amsterdam, going to Calgary and back, is 1 ton of CO2. Okay? A Dutch, and I think also a UK person, emits about 11 tons CO2 per year. Think, okay, 11 tons. I have also to say that every day you breathe CO2. Remember, you build up from carbon. You eat carbon-based products. So you will have as exhaust CO2. So it's about 1 kilogram per day. So about, depending on the person, 300 to 400 kilograms CO2. You cannot do a lot about it. That are the facts of life. When you drive 35,000 kilometers, 5 tons. You see? It adds up. I'm traveling a lot. So it means I'm a big emitter. People in the US and Canada, 16, 17 tons CO2 per year. On average in the world, 5 tons CO2. Yesterday, I came here by train, left Utrecht, and went via Brussels to London with the train. Well, the first thing is that you can see that here you can notice that it was indicating that it was CO2 neutral, at least claimed by the train company. So that means that we have been not emitting CO2, and as you can read, it's indicated that the electricity comes from wind to solar panels. The first observation is that the price coming by train was more expensive than taking a plane from Amsterdam to London. That's surprising. And it is because we have to admit that we do not take into account the whole price. That means that somehow it's strange that we pay more for a ticket by a train than with a plane. And part of the reason is that our legislation does not take into account any, and not yet, the CO2 emissions. It does not treat CO2 emissions as something really important. So the question is, should we do similar to what we have been doing for introducing the catalyst, exhaust catalyst, which was introduced by legislation? Maybe it's time also to consider if we have to think about legislation which helps us to make this transformation happening. So this electricity comes, for example, from wind and solar panels. Now, we also have to see to take this picture into account. And what I want to say with this picture is that the sun not always shines. You have fluctuations. In the summer, the winter, day and night. And the wind is also not always blowing. And it depends really locally if you have really good electricity production or renewable electricity production. Secondly, you may not forget we still have to reduce because we still have this molecule in our air, 400 ppm. So we have to reduce it. So how do we do that? So we have to try to reduce the CO2 and convert it into something useful. And for this, I would like to state that we have now this molecule, carbon dioxide, which has one carbon. And remember that this molecule, for example, is what we currently use as a fuel molecule, which consists of many of these carbons. You agree? So we don't need, at this stage, this, but we need something to glue carbons together. So the catalyst should not be a scissor, but something which brings together carbons, and carbons which are linked together and makes a new molecule. For this, I have an experiment. I'd like to show you a short experiment to illustrate what I want to say with this. And I start. CO2, which has the solid form of CO2. So this is solid CO2. What you can do is you can add now. And now you see that CO2 is released. We have to add a catalyst. And this is catalyst. So we can add with catalyst. And now, out of this, we make molecules. And one of the molecules which you can make out of this is, for example, methane. And that's a hydrocarbon, which you can use for certain things like heating, and even you can use it for driving a car. So, I would like to continue now by showing what you can do with the CO2, because this experiment where CO2 and water with a catalyst is giving something is already reality. I went some weeks ago, I went to Germany, to Werther, near Bremen, and there you can find this plant. They use from CO2 from the Bremen city, and they brought it there in a small village city of Werther. And there with a catalyst, they convert it to e-gas. It's gas made from electricity. And this is the reaction where we have CO2 plus hydrogen gives methane. So what you have is nothing else than CO2 plus hydrogen gives this molecule. And this is a reaction which currently works. You can argue and say, but if we have this already, what prevents us then to implement it? Well, the factory which I showed you there in Bremen is currently not making a lot of profit. Again, because of legislation. Again, because it has to compete with these fossil resources, which are much cheaper. So that is where we are working on. We want to work on this reaction to make more efficient catalyst part to enable this reaction. But also, we want to make sure that we make other molecules out of methane. Because methane is useful. And it would be wonderful if you could make the materials which we currently use to have the berry, which we currently make out of, for example, this barrel of crude oil.
Produces sustainable fuel from CO2. Right now, society mainly uses fossil fuels to produce our chemicals, fuels, and electricity. Basically all synthetic products we use every day. By burning fossil fuels, carbon dioxide is released, and we're rapidly warming up the Earth. We want to replace fossil fuels by sustainable resources, for example, renewable electricity. But the sun doesn't always shine, and consequently, we'd like to be able to store large quantities of its energy, for example, in summer, to be able to use it in winter. In my PhD research, I want to solve both of these problems, carbon dioxide emissions, as well as the current difficulty to store electrical energy on a large scale. There could be one solution to help solve both of these problems. Using CO2 and sustainably produced electricity to produce other molecules, such as methane. If we use CO2 from point sources like factories, together with hydrogen that's produced by splitting water and using renewable electricity, we can make methane. This conversion is enabled by a catalyst. In my research, the catalyst is a nickel nanoparticle. Nickel is a cheap and widely available metal, as opposed to noble metals such as platinum, for which this reaction also occurs. We try to use sustainable materials to facilitate the transition towards a green, circular economy. In the next coming years, we'll investigate how to create other value-added chemicals from CO2, like methanol or ethylene and propylene. This way, in the future, we may be able to use CO2 as a sustainable fuel.
If research, like what Charlotte explained, can become reasonable. They also make other waste. This is something what you have in your kitchen. At least, this is what we have at home. And this is made out of polymers, biopolymers. Polymers like cellulose. And here I show you lignin. Now what is a polymer? A polymer is nothing else than a repeating unit. And a repeating unit is shown here. So a biopolymer or a polymer is a unit which you can just continue. But you can continue, and here the long chain of this holds for lignin, cellulose, of mathematics. My name is Matt Parker. I used to be a maths teacher, which is why I know that person is on their phone while I'm talking. Honestly, once a teacher, always a teacher. So can you all hear me adequately loud, amplified through the microphone? Excellent. People at the top are all happy. Marvellous. Right, so the plan for tonight, as Peter very kindly said in his introduction, and then went home. No, it's Big Bird